Imagine sitting in your room on a warm afternoon. As the temperature rises, the fan beside you automatically speeds up to keep you comfortable. And when it cools down, the fan quietly slows down, saving energy, all without you touching a button. This is not just convenience, it's smart automation. Today, we are going to show you a smart PID control with AWS IoT on PIC32CM JH VL Curiosity Nano Plus Touch Evaluation Kit, where a motor speed is intelligently controlled based on real-time temperature and the data is seamlessly sent to Amazon AWS Cloud for monitoring and control. The PIC32CM JH VL MCU is based on ARM Cortex M0 Plus core, comes with a rich set of peripherals. This application demonstrates an automatic fan control using PIC32CM JH VL Curiosity Nano Plus Touch Evaluation Kit, combined with a temperature and humidity 13-click sensor, a R&W F02 Wi-Fi module to connect to AWS Cloud, and a motor driver board. The motor speed is managed using pulse width modulation (PWM) generated by MCU's timer counter module. For stability, here a proportional integral and derivative PID control algorithm is implemented. PID ensures the motor responds quickly, eliminates error, and maintains smooth operation. Download the MPLAB Harmony v3 repositories and install the required software shown here. You can use MCC Content Manager to download these Harmony packages. Serial monitoring can be performed using applications like Term. If you are new to MCC, check out the video linked in the description. This demo supports two operating modes, automatic and manual mode. In automatic mode, the motor speed is controlled using a PID algorithm. As the temperature rises, the PWM duty cycle increases, causing the fan to spin faster. Conversely, as the temperature drops, the fan speed decreases, ensuring optimal energy usage. All these adjustments occur seamlessly without requiring user intervention. In manual mode, the user can override the automated control and directly set the fan speed. 3 levels of speeds are available: low, medium, and high. The transition between automatic and manual modes is managed through the message payload sent via AWS, giving the user a full flexibility on operation and control. All sensor data, including temperature readings and fan status, is published to the AWS IoT core using the R&W F02 Wi-Fi module using MQTT protocol. From the AWS console, user can monitor live temperature data, view the current fan operation status, and send control commands to switch between automatic and manual modes. To achieve this, we will set up the hardware, download the project from the kit page, open the project and launch the MCC, check the peripheral configurations in the MCC, then compile the project and see the output. Now let us set up the hardware. Mount the PIC32CM JH value line kit on the Curiosity Nano baseboard. Mount the temperature and humidity 13-click on the Microe socket 1 connector of the baseboard. Plug the R&WF Wi-Fi board on the Microe socket 2. Connect the PIC32CM JH value line kit to the host PC using a USB Type-C cable. Connect the pin 8, PWM3 and pin 19 ground in the Explain Pro extension kit of Curiosity Nano baseboard to pin M1A and pin ground of the dual-channel DC motor driver MDD3A respectively. Please note that since the Wi-Fi module operates on 3.3 volt, the operating voltage of PIC32CM JH value line kit is changed to 3.3 volt instead of 5 volt with the help of MPLAB project properties. Navigate to the kit page and download the project from the software section as shown here. Extract the demo firmware and open the project using the MPLAB IDE. Right-click on the project and set it as the main project. Next, launch the MPLAB code configurator to view the pre-configured peripherals. The TC3 timer is configured as PWM generator and drives fan control with duty cycles updates coming from the PID loop or the MQTT command. The SIRCOM2 is configured as I2C, managed through the Harmony I2C driver interfaces with the HTU21D sensor to read temperature data. The Power Manager PM ensures low power efficiency when the modules are idle. PTC provides capacitive touch sensing used as a user input, triggering MQTT events. Timing functions come from the RTC for system wake-ups and timestamps, and the system time service schedules periodic tasks such as sensor reads, PID updates, and touch processing. The SRCOM3 UART connects the sys console and the sys debug services for logging and diagnostics, while SRCOM0 is configured as UART. Connectivity is handled by the RNWF Wi-Fi service, which manages SSID connection and reconnections, supported by the RNWF Net service and the RNWF MQTT service, which links the application to the AWS IoT core for telemetry and remote control. The system uses the 48 MHz internal oscillator as the main source for the CPU and supports performance-critical components such as SRCOMs, PTC and Wi-Fi. Under the pin configurations tab, you can see the various pin configurations used in this project. You can review the project files to understand how the code is implemented. You can also use MCC to add new peripherals to your application. Under project properties, ensure that the connected hardware tool is recognized as the PIC32CM JH Curiosity Nano Plus Touch Evaluation Kit. To build and flash the firmware, click the Make and Program Device button in the MPLAB IDE. The programming will take a few seconds, after which the device is ready to run. Open a serial terminal on your PC. Select the COM port of the board and set the baud rate as shown. Next, we need to reset the device. Open a command prompt and run the following command as shown on the screen. This command is available in the MPLAB IP installation directory. Once executed, the board will reset and start its initialization process. The device connects to the Wi-Fi using the predefined credentials. The default SSID is demo AP and the password is as shown on the screen. You can set your Wi-Fi router or mobile hotspot to these values. There are two ways to configure credentials in your project. Open MPLAB Code Configurator, select the RNWF Wi-Fi service and enter the SSID and password. Second option is through the manual configuration. Go to Project Files and open the configurations.h file in the main project and edit these lines. You can change the SSID and password, then save and rebuild the project to generate the code. Once the device resets, you will see initialization messages on the serial terminal. When the connection to the AWS IoT core is successful, the terminal will display Press Touch button to start publishing. Now, let's move to the cloud side. Log into the AWS Management Console. Go to IoT Core and open the MQTT test client. Under Subscriber topic, type Smart PID AWS as shown on the screen. Click on Subscribe. This will allow you to monitor live messages published from the device. When the terminal message appears, simply place your finger on the touch button of the Curiosity Nano board. Immediately, temperature readings from the sensor will be published to the AWS IoT core. Here, you can see the live data streaming in the MQTT client. By default, the demo runs in the automatic mode. You can also check the manual control. In the AWS MQTT test client, publish the following JSON payload. The fan now runs at a low speed. Similarly, you can choose medium and high by changing the speed value in the message. To switch back to automatic PID control, publish the message as shown on the screen. The fan will now adjust its speed automatically based on the temperature. If your room has a different baseline temperature, you can adjust the set point. Open the app_pid.c file and update the set temperature macro, and that's it. The demo is now fully operational. Explore more demos and projects for the PIC32CM JH MCUs by visiting the MPLAB Discover page. Visit microchip.com/harmony to learn more about MPLAB Harmony v3 videos, tutorials, and demos. We hope you enjoyed this brief demonstration. Thanks for watching.